I'm not happy with the cave at 300 kelvins. So probably, I don't know. Next time I'll try to investigate how I can produce a better cave, or what range I should use for a better cave at 300. Because the one we have at 300, I'm not happy with it. Okay, so help SciPy dot integrate. Okay, so with SciPy.integrate, our interest is SciPy.integrate gives us, as we saw, access to a bunch of integration functions. There's quad, there's down here, there's what we are familiar with, Simpson. This trapezoidal, I think we can do with Simpson. So we can just say import Simpson from SciPy.integrate. So, import. Sub module from can do that. So we saw how to use this. You just give it you can ask for help on how to use it. Yeah. So with Simpson, we just need to put in our y values. Then if we have got our x values, we can put them there. In this case, our x values are just the wavelengths. So you can put in our spectral values for the caves, which produce the caves, and that. So we are supposed to do an integration. If you recall from your notes, if you have got the notes with you, we are supposed to find the total emissivity power by integrating the area under each cave. Show that it confirms with the Stefan Boltzmann law. I don't know how you're going to show that it conforms, but we can work out what the integral is. So in this case, seems the spectral emissivity you put in your y bit and your x, so your y is your spectral emissivity power at 7000 for the first cave. If you do that, what do you get? So this is what you get as the area under that. How you move from there, I'm not pretty sure how you're going to do the confirmation. Similarly, For the 5,800, you get this. Then for your the other bit, that's what you get for 300. So this is the area under the caves. That is for 7,000 kelvins, for 5,800, for 300. We have got something very small. Like I said, I'm not happy about the cave for 300. So probably we might need to change something to see more information about the 300 cave. But on the integrations, this is how you would work out the integrations. Calculate the area under the caves. Under the 7,000, okay, 5,800, okay, and 300 caves. Blackbody caves. Okay. So what I'm not sure about is we have the area, fine. What I'm not sure about is the part where we say how does it prove the other bit. Any ideas?
The question again, Mr. Litton.
There's the B part of your lab, the Blackbody cave lab. Part B says find the total emissivity power by integrating the area under each of the caves. We have done this bit. Show that it conforms with the Stefan Boltzmann's law. How does
that one we have to use the formula for Stefan Boltzmann law, I guess, to compare with the integration.
Okay, so where is that? That's where we have BT is approximately equals to sigma multiplied by T4.
I'm sure it is.
Sigma T4. Okay, so we can do that. Our value of sigma, we have a value of sigma. I have 5 point in your notes. Sigma is 5.6697 times 10 to the power minus 8 watts Newton meter Kelvin to the power 4. So we can do that. Okay, so let's see. Okay, so those are the integrations. So create a lambda for Stefan Boltzmann's law. Or just a function. Create create a function. What's my multiplied by 2 to the power 4. Then sigma is, sorry, where sigma is 5.66 97 times 10 to the power minus 18 minus 8 minus 8 watts into the power minus 2 to the power minus 4. Okay, so you can see define Stefan Boltzmann law. So you need a temperature in kelvins. So retains the spectral emissivity, spectral emissive power according to Stefan Boltzmann law. So here we need sigma. Sigma is 5.6697 e to the power minus 8. Then we need our b. So our b, calculate emissive power so b is going to be equals to sigma times t to the power 4. Then you retain b, right? I think return b. So what? Okay. So let's see. Stefan, for t equals to 7,000. Okay, Does it match for 7,000? For 7,000 we have this bit here, then there, 130 million. Yes. Then here. Okay, so that one has got 130. This one has got 136.
Yes.
So I think practically, yes, it's consistent. Are we clear? Remember, the Stefan Boltzmann law is an approximation. Are we clear?
Yes, sir. I think it is consistent.
Yeah, it's not exact, but it's consistent. So basically, what we need to do, I think, yeah. So for Stefan's law at here, Stefan Boltzmann law at, so not exact but very consistent, I think, in my opinion. So yeah, for 7,000 things are good. Then for 5,800 5,800, so we say Stefan's law T 5,800. We have this bit here, then there 64 million. So we've got 64 million. For the other one, we've got how much here? No, this one is supposed to be 5,800. 5,800. So here we've got 61. So here we've got 61 million watts of power. You could actually do the following, kind of like, yeah, basically, okay, there is someone who's trying to enter, okay, or someone has left. So this other side we have at 5,800 we have got 61 million. Okay, then when we use Stefan's law we have got 64 million. So again, the keyword is consistent, so I think it lines up. Is that clear? Now the key thing which we are worried about, the one thing I'm worried about is the one at 300. If what we have makes sense or not, doesn't make sense, I don't know. So at 300, which is at room temperature, so Stefan's law, T equals to 300, because our cave looks funny at 300. Yeah, so there's a problem at 300. So our cave is probably not complete at 300. So we need to do something at 300. You can see Stefan's law at 300 is giving us 459, or basically 460. But if you look at what we have plotted at 300, and what our integration gives, what we have plotted at 300, our plot at 300 is kind of funny. It doesn't look nice. Here, this is a 300 cave. So I think what we need to do a bit of research before we proceed. We're going to shift to, I'll share a tab where we're going to go to Google, then we're going to look for what range to use for 300. Okay. If there is such a thing. Okay. So Blackbody cave at 300k. Okay. Hope you can see.
Oh. I think it's 3,000, not 300.
Ah. So it's supposed to be 3,000, not 300, huh? Can someone confirm? Is it 300?
I think whatsoever, if it is 300,
It's supposed to be stick about.
so then under that same thing, it is still consistent with the. It is still, even if it is 300 Stefan Boltzmann, so I think it's just not good at low temperatures to produce the graph, I guess. I think 3,000 can do better.
Okay, let's try 3,000 and see what we have. Because we have got 5,000, we've got 400, we've got 4,000. Let's see what happens at 3,000. So let's get back. Then we'll come back to 300 if whatever it is makes sense. So this is for, okay, so copy this, copy paste. Okay. What do I have? What have I done? So we have 5. So we have these at 7. Then you got 550, 5,800. Then this one's supposed to be for 300. So let's put in 3,000 here. So 3,000. Then this cave here. With up a bit. So this is going to be for 3,000. So for 3,000 is this. Then if we put them together with 3,000 instead of 300, no, what do I have? There is a small, so for 3,000 you can see there is a small, it doesn't seem to work very well. Okay, you can see the cave here, okay, which has come out for 3,000, This is a Blackbody cave for 3000. Okay. But there is still stuff going this side. So it's not as if it's at 0 or something like that. So I don't know if we can extend this thing. If we can extend it to where we define the function AB 3000. If we let's try to extend it to, let's try to make an yes.
I think these things, they doesn't go to 0 matter what.
It doesn't what?
The caves, they don't go to 0.
No, they never really go to 0. So that's why I want to I want us to extend the wavelength. Okay? Because it's starting at we have got wavelength in, as you can see from here. You've got wavelength in what is in micrometers. So we're starting from we can start from there, or you can start from 0 if that's what you want. But 0 might give us a problem. So we started at this point, which is somewhere 100 or something like that, whatever it was. We started at this point. Then they don't end this side. They don't end at 3. So probably it goes further than 5 or 6. So let's try to so if I share this bit here, you don't at 3 here, it doesn't end here. But most of the energy is between this point and this point here. Whatever this is here, somewhere 0.25 micrometers to somewhere 3 micrometers. So most of the stuff is happening in between here. So if we try to extend to, let's say, 6 micrometers, let's see what happens. If we get a different result or something which makes sense. So share this bit here. So inside our function, this is our Blackbody spectrum function. Inside our function, the wavelength ranges were hard-coded from 100, whatever this to that. So we'll change this to, let's change it to 6. Like that, okay? Then that. So when we do that, so this is what we get for 7000. This is how our cave comes out. If you move to 6, so you can see there's nothing much happening. If you move from 3 here, all this bit here, for these cases, we don't have a lot happening. For 550, it moves the side. We move to 6. This is for 3000. It moves up to that point. Then this is for 300. The 300 one is still going. So maybe there is, you can see it's still rising this side.
Yes.
So we might have to increase the range. Let's go back and increase the range. Because we need to come up with something which is consistent with what we are getting from the Stefan's law. So instead of 6, let me put 20. We see what happens. Okay, so there's a squeeze there, there's a squeeze there, there's a squeeze there, 3000, there's a squeeze, 300. Okay, so we're getting somewhere. So that is a 20. So you can see for 300, there's a 10. You see that?
Yes.
Yeah, so basically we had a very small bit of the 300 cave. So we need to probably increase the range. You know, what this is showing is that maybe our textbooks are not very correct. Okay? Because from whatever people get from the textbooks, it kind of shows that maybe within 300, for the 300 cave, you can get it between, you can get the whole cave between what is 0 and 3 micrometers, but that's not what you're saying here. So I think from what we have here, we still need to extend the 300 cave. So I'm going to double, because it's a 20, I'm going to double to 40 or probably 50. So here, I'll go to 50. So there's a squeeze. And I think here you're seeing something here. So we need a way of entering information about the wavelength in our function so that we can accommodate everything there. So the 300 finally goes a bit down there at 50 stuff. Let's increase that a bit again. 100. Let's go 100. Okay. So we've got something which looks like something at 300. Okay, that's fine. So now if we start doing what we've been doing. So they're very squished. You still don't see a lot, but that's okay for now. We want to see, the only thing we are kind of very much interested in is what we get now from the integration, and what we get, whether what we get from the integration at 300 matches what we have with Stefan's law. So here it's at 300. Okay, so now we get 444 watts. And with Stefan's law for 300, we got 459. So I think that smells like consistency to me. The only thing you can see here is we need to be specific about the ranges we're entering. So for the other high temperatures, between whatever we have up to 3, we get very good caves, which are which are consistent. Between 3 and 6, we get good caves, which are consistent. But for the low temperature ones, we need a cave which goes all the way probably up to something like 100. So what we need to do is we need to adapt our program, our function, our Blackbody function. We need to adapt our Blackbody function so that it can accept temperature and wavelength. Now, how are you going to do that? I can do the following. I can ask if the temperature is above 1000 and below 1000, then we can use a different wavelength range. Are we clear?
Yes, sir.
So we can say just inside the function, you can say if temp is greater than or equals to 1000, then we can use a different thing. Else why? I don't understand why it's not recognizing our if. See if it's going to work. Does it run or not? Okay, seems to run. Let's see what we get. Okay, so with this if we have put here, you've seen the if we have put here, saying if the temperature is greater than 1000 kelvins, then use this range of wavelengths from 100 to 3 from 100 micrometers to 3000 micrometers. Okay, otherwise if the temperature, if it's not greater than 1000, then you use this range from 100 micrometers to 100,000. That should allow us to see the other curve for what is the one for the 300. So our function should be able to work for high temperatures. It should also be able to correctly produce things for low temperature things. If we add just this little if here. Are we clear? Let's see if it's going to work, if it's going to produce the desired stuff. Right now we've got a good curve for 7000. That's fine. So it's going up to only 300. 3000 kelvins, 3000 micro. 3 micrometers from hundreds, whatever that a bit, only to 3 micrometers, and our so I don't think we need this. Okay, fine. So it's working for high temperatures. We have got our good curve. Then we move to another high temperature, but slightly lower, 5800. Okay, now a better curve has come out. Okay, then 3000 here. Okay, 3000. That bit has come out, so there is kind of a bit of a deficiency. I don't know whether we should go up to 6, or I think 6 is better, but we can make adjustments. Then let's see if it's going to work for 300. For 300, okay, now it works. Are we clear? Yeah, so for high temperatures and low temperatures, we're getting better curves. I think the only little adjustments we need to make is we need to shift the range not from 3 but to 6 for the high temperatures, or 6 or 10, whichever one is better. Here, let's make it at 6 and see what you get. Okay, again. Okay, that is at 6. It's good. That's another 6. Okay, that's better. Even 4 I think would work, as far as I can see. So there is really no need for us to go all the way up to 6. Then that is 550 or so. Yeah, So 6, we are overdoing things. I think you can go up to 4. At 3, let's see. Oh, okay, fine. 6 is good for even here. So I think that's good. Okay. Then at 300. All right, there we are. So that's the one at 300. So we've produced a cave at 300. Then this one we already did, so we don't need it. It's going to be difficult to plot them at the same time, on the same scale. Basically, I don't think it's possible since they've got different ranges. We can try, but I don't think it will work. And if you do that, the other plots are not going to be visible. The 300 cave is not going to be visible. You can do that. You can try. Okay. So you can see there's a squish. So the other things, you can't see them. So I don't think it's possible to plot these caves together. Okay, we have got something here, or the other bit here. So there's a 7,000. You can actually do it, but the other one is kind of squished. You can't see anything really. There's a 7,000, which is the blue one. Then there's a 5,800, which is the orange one here. Then there's a 3,000, which is this bit here. Then there's the other one, the 300, which is just there at the bottom squished. So you can't really see it. Yeah. So it's very difficult to see the other bits. If you put them together, then you end up with stuff that doesn't look nice. So I think it's better you just draw them separately. So in this case also, since, let's see, what does our integration give us? Is there any improvements? That is what. Why do we have a different value? Okay, we have different things now. The only thing I can see which accounts for this difference is the fact that we went further to 6. Just a minute. Okay, so we go back. Range 6 up to 6 is too much, I think. Let's cut it at 4. Where's the function? Let's try to cut it at 4. Or 3.5. Okay, so I think we've got a different problem here. The different problem we have why the thing is not working out properly. When we work out, remember our wavelengths are no longer the same, so we're no longer dealing with the same wavelength all over the place. So I think what we need to do is where there is a bit where we are returning the wavelength, we're also getting the wavelength. So here we say wavelength 7000. We need to do this. The wavelength at 7000. Then here also. Okay, so the plot comes out. So we have, for whatever, whether it's high or low, we get a value of wavelength at 5800. Because I wasn't understanding why the integration suddenly is failing. It's giving us terrible things. Because at the end, in the integration, we are using the same wavelength, but the last thing we do is 300, which means the wavelength is different. Okay, but we'll see if it has an effect. Okay. Next. Here. Then we enter 300. Okay. Then in our integrations, I don't think we need this. Don't think this is needed. So we're plotting against wavelength at 3 at 7. Wavelength at 580. Wavelength at 3000. Wavelength at 300. Okay, so we end up with that. So that's how we concluded that not good for plotting together. Okay, just a bit. Just checking if people will follow. 5800. $3,000. Yeah. So when you do our integrations, decide so here wavelength at 7000. Okay, now I think it works better. We compare that with 7000 with what we have for this Stefan's law. Yeah, so now it works. So you've got 136 million or gigawatts. Then here now it works. You've got 131 gigawatts. Now it's consistent. So this bit here also, wavelength at 5800. Okay, now this is 61, and The other bit down there is 64. So now things are working properly. So our change in which kind of what kind of range to use has necessitated this change in how we are doing the problem again. The wavelength at then there's this bit here at 3000. So that's 42. 3000. 42 million. Then you got a 3000 here. I think it's 45. 45 something. So that's also consistent. Then we come to our last cave, 300. So our 300 cave, oh sorry, 300, okay, that's this. Then for the other bit, 300, so this is what you have. So okay, fine. So what we have shown, the first thing we've done is we have done the integrations. Of course, we have had to make modifications to our Blackbody function so that it can accept different, depending on what the temperature is. If we are classifying a high, if we're talking about a high temperature, if the temperature is high, then we have used a different range of wavelengths. If the temperature is lower than 1000, then we have used a different range of wavelengths. And those wavelengths which you have used, we have given them, we are returning the wavelengths and storing them as particular variables, as you have seen. Wavelength 7000K, wavelength 5800, wavelength 3000K, wavelength 300K. Okay. So this is just basically one implementation of how you could do the second part. Of course, a recording is being made of this thing. When it comes to you doing this problem, this lab, choose. You can't give me everything which I've done. Okay, let's be to the point, then choose whatever you have to choose from this, then you give us what we have to do. Okay, so I believe the second part of the lab has been done. We have just finished the second part of the lab. So the first part was use the Planck's Blackbody radiation cave to draw the Blackbody radiation caves for 7000, 5800, and 300 kelvins. That bit has been done. We also added another cave for 300 kelvins, so that one has been done. The part B is, then it says, then for part A, the caves, plotted the three caves on the same page on a common set of axes. That's not possible. We have just found out that that's not possible to do. If there are difficulties, yes, there were, due to caves being separated by large distances. Yes, you should draw the caves on separate pages. So these caves are supposed to be put on separate pages. So that's the other thing we've agreed on. Part B, find the total emissive power by integrating the area under each cave. We have done that. We have used Simpson. You could use other ways of doing that. That's up to you. There is trapezoidal, or you can stick with Simpson. That's fine. Show that it conforms with the Stefan-Boltzmann law. We have done that. Part C, find the maximum for each of the caves and show that it agrees with Wayne's law. Now for each of the caves, find the maximum for each of the caves. For each of the caves, you can find where the maximum lies. Okay. you can find where the maximum lies. So you can get the maximum, you can get the coordinates of the maximum and also the maximum using so you're going to say getting the maximum value of an array of a numpy array, I think with np.argmax. This bit, I think this should be able to give us the coordinate or the index where the maximum is, and later on we should be able to use that. So let's say maximum, let's say np.argmax spectral 7000. What do we get? So 7000 maximum, the index is this. So we can do the following. Max index okay, say index of maximum, index of max there. So with that, now you can use your spectral 7000 index of max at 7000k. You can do that. This is a list, an array, so I can say index of max at 7000k. So the maximum is here, so the maximum value is there. That's what the maximum is. Is that clear? Hello?
Yes, it is.
Yeah.
It's clear.
So you can get them. You can get the index if you've got an array. You can use this function argmax to get the index of the maximum. Okay. Then you can use that index, put it back in this array so that you can extract what the maximum value is. Then Vin's displacement law. Vin's displacement law. Let's do the following. Vin displacement law states as follows. So begin. So Vin's law. I saw something in the notes. Yeah, I think this is what it is. Yeah, the following. Lambda m max for max is equals to defrag the temperature and what is it I'm looking for? So we're looking for the wavelength where the maximum value is, right? Okay, that's fine. Then what is the wavelength in this case? We're going to say wavelength at 7000 index of max at 7,000. So it is at it's this. So in this case, so this is where the maximum exists. This is the maximum value of the cave, and this is the wavelength at which the maximum is. So with this Vin's law, oh sorry, something is missing. There's a number 2898. 2898. This expression gives you whatever you think is supposed to be. So we can create a function, define Vin's displacement law. So the only thing we're going to get is the temperature. Then here the dock screen is return the wavelength of maximum at temperature at temp. So we're going to say maximum wavelength is going to be equals to 2898 divided by whatever the temperature is. Then return maximum Okay, so that's Vin's law. So for our case, when temp is 7,000, that. So we have that. But in what units? There's something which is the same, but what units are this thing in? Just a minute, I'm looking at your notes. Anyone have an idea what the units are supposed to be? Because what we have and what has come out from our thing, they're not the same things. I think the units should be in micrometers. If it's in micrometers, then it makes sense. If this thing gives you wavelength in micrometers, then it makes sense.
The one is low, I think it is in...
The other one is in meters. This is in meters.
Okay.
This is in meters. The question I'm asking is, what is this? What are the units of the wavelength of this thing? Is it in micrometers? If it's in micrometers, then it makes sense.
It's either micrometer or nano.
Your notes don't say much. I think it's in micrometers. Yeah, I think it's in micrometers. Let me do another Google search. Then let me share my Google search. Vin Vin's displacement low units. Yeah, so Professor Jane, the equation which Professor Jane gives, you've seen this?
Yes, it is micrometers.
So it's supposed to be micrometers. So our expression, so we're supposed to multiply, I think, by, supposed to be like this, not just 2.8, so whatever this is. The whole thing is supposed to be this times 10 to the power minus 3. So let me go back. So this gives units in micrometers. Where lambda m is in it's in micrometers. So if that's the case, then whatever we have here, we can multiply it by times 10 to the power. Is it multiply or divide? Let's see what you got. What do you? Yeah. I don't know. I'm not sure. So if this is in micrometers, if this is in micrometers, then this is in meters. So we end up with what? This bit, yeah. So it makes sense. This is just 0.416 micrometers, right? What you have here is 0.416 micrometers. Then what we have here is 0.414. So there is 0.414 here. The other one is giving us 0.416. So I think things are okay. So this other one retains the wavelength of at maximum temperature in micrometers. That expression here, there. Are we clear?
Yes, sir.
So if you want it in meters, you multiply by 10 to the power, sorry, micrometers, 10 to the power. If you want it in meters, I made a mistake. If you want it in meters, you multiply by times 10 to the power minus 6. When you do that, then you get, yeah, there it is. Here, 4.14 e to the power minus 7. And here we have basically same 4.167, which is just 4.1. What this is 4.117. times 10 to the power minus 7. Is that clear?
Yes, sir.
Yeah. Next, we check for the other things at 5,500, 5,800. So we copy this, bring it down, 5,800. Index at 5,800. Then what is the wavelength at that 5,800? What is the power first? What is the wavelength? At 5,800. There. Then the wavelength at 5,800. There, that's your wavelength at 5,800. Then when you do Wien's law, at 5,800, so there's a, here we have got 5.03, here we've got 4.996. This is just 5. This bit is just 5. So basically, you've got 5.0. This is 5 times 10 to the power minus 7. Then this is also 5 here. Is that clear?
Yes.
Yeah. So things are working out. Then we move to the other bits. 3,000. So at 3,000, you get your maximum index, then you put it here. You get your power, that's your power, then the wavelength, there. Then we use Wien's displacement law at 3,000. There. So we've got 9.7. Then 2, whatever it is. So basically it's just 9.7 times 10 to the power minus 7. Then this is 9.66, which is just about 9.7 times 10 to the power minus that. So things are adding up nicely. Then lastly, what have I done? 300. Okay, wait a minute. All right, that's my Jesus. I need to charge my phone since I'm using MTN mobile data to hotspot my computer. All right, there we go. So we're almost at the end of this lab. So max that, then what's the spectral, what's the maximum value at that bit. Then the wavelength. What did I do? Hey, where to get this? So that's our maximum wavelength at 300. The next bit is for us to use Wien's displacement law at 300. There. So here we've got 9.73, here we've got 9.65, which is just about 9.73, and everything is consistent. Okay. Those are the three things we're supposed to do. Any questions?
No question, Mr. Fisson. I think you have explained everything very well.
I'm one to figure. Four.
I'm being honest. I'm being honest.
Okay, that's good. So there's a record. We're going to, again, we have been recording this thing, so we're going to post the recording on YouTube. So it's up to you guys. As far as I'm concerned, at least I need one lab from you. Then I'll go through the notes. We'll look for the next lab which has to be done. Then we'll see how we can do it. So between now and next week, I should be able to check out which lab is the second one and see how we can proceed from there. Okay. So with this whole thing which is there, choose what you need for you to answer, to do the tasks which are in. Don't show me how we struggled. We go through. Choose what is necessary and do your stuff. Are we clear?
All right.
Yes. Then after you're done, please do not copy from your friends. There is no need for you to copy. You only copy when you are stuck. But there is no need for you to get stuck in this case. Okay? This is also an opportunity for you to learn how to program and also how to practically use what you have learned with Python. You have been learning Python last year, but the problem with last year is we did not have a good opportunity for us to actually do the Python. Okay? Your friends this time around, they will have a better opportunity to see how you can use the Python to do stuff. So please use this opportunity to actually learn. Are we clear? As far as I'm concerned, this course is going to come to an end when the labs get done. Okay? Once the labs are done, then things come to an end. Then you give me your stuff. Me, I don't have a problem with people getting everything. If you get everything, good for you. Okay? But if you do rubbish stuff, then you expect to get everything. Being lazy is not going to help you. I'll give you 0. The reason why I'm going to give you 0 is because we gave you all the tools to get everything. Then you choose to do poorly, then that's not going to be acceptable. Are we clear? The notebook, the PDF, especially the PDF, I will not give you the notebook. I will post a PDF on this PDF, this PDF will post it on Moodle. So it's up to you to choose which code fragments you want to pick, then make your own thing together, let it work. If there's a problem, go back, watch the videos and see why it's not working and stuff like that. Then once everything is in place, you send me. Then we mark. We give you all the marks or we give you 0, whichever one you choose. That's up to you. Okay, but on our end here, on my part, we are going to try, no matter how long it takes, whether it takes us up to December, we are going to try to make sure things get done. Are we clear?
Yes, sir.
Yes, that's the spirit. You do things up to the last minute, but make sure what you have done is the best which you could have done, and there's no other way. I don't like people coming to follow me up saying, no, please forgive me, I'm begging, I'm on my knees. I hate people who are on their knees, because it's not necessary for you to be begging someone when you have been empowered with things. There's no need for you to beg. If you find yourself in a situation where you're begging me for something, you get. So let's not do that, huh? On my end, I will do the best I can. You do the best on your side, so that you get all the marks. Okay. So I think we are done here.
Sir, just to be clear, you said you share a PDF of the notebook?
Yes. I will not give you the
Okay,
notebook.
alright.
I will share the video of the notebook, but I'll also share the PDF of the notebook. But I will not give you the notebook. Yeah. We can probably also put the thing there also. I don't know. Whatever it is, I don't really care very much. All I care about is people learning. Yes.
I think for her, she's under Austria. She's not on Moodle. Isn't it?
Okay. So then in that case.
Yes, it's true.
So in that case, then I think also on the WhatsApp group. Okay. All right.
Thank you.
Yeah, just. So we are done here for today. So this lab is finally done. I'm happy about that bit. And thanks for attending. See you next week.
See you.
Cheers.
See you, sir. Bye-bye.
Go ahead.